All right, so continuing on, now we're going to talk about quantum mechanics. This is what we got by combining all that previous work, seeing what it all means, how does it all fit together. So we have this gentleman, Erwin Schrödinger, who developed a mathematical treatment. We call it the Schrödinger equation, which helps account for both the wave and the particle nature of electrons. And so that brings us to quantum mechanics. And so the idea is that Schrödinger's equation gives you a wave function for the electron, an idea of where the electrons acting as waves can be. What's the probability of finding one there? What's the energy value there? So if you kind of put it all together, it's what is the probability of finding an electron given an energy state, right? And so we have these plots like here, which is at any given moment, here is where an electron could be. As you see, well, where there's lots of dots, that's high probability. Where there's not many dots, that's low probability. Right? Well, solving his equation gives us some what we call quantum numbers, a set of mathematical descriptors that describe where the electron could be. And those wheres, well, we call them orbitals. Niels Bohr would call them orbits because he just had his circle radii going around the nucleus. And so we adjusted the language here to say, well, now it's an orbital, but have a certain amount of energy. That orbital describes a certain distribution of electron density, a certain shape, a certain orientation in 3 dimensions. And so an orbital itself gets described by 3 quantum numbers. Now, quantum numbers, not on the AP test. They actually removed them a few years ago, but a lot of colleges still teach them. If you're happening to be watching this for my Carroll Community class, they're on your test for this chapter. And so to kind of get people ready, we're going to address them here. In the high school class, we won't address them in class until after the test. But I just want to include it here with this chapter so we can see, okay, it all goes together. This is something that you will be using at the college level probably. And so our first quantum number is the principal quantum number. We give it the symbol n. This tells you the main energy level for the orbital. And these correspond to the Bohr model. So Bohr said it was 1, 2, 3, 4, 5. So the n levels are 1, 2, 3, 4, 5. So it's the values of n are integers greater than or equal to 1. So 1, 2, 3, 4, 5. Basically matching up to the rows on the periodic table. Right? The second quantum number is the angular momentum quantum number, which is given the symbol lowercase l. This number tells you which type of orbital. And so for the type, we mainly go by the shape. The allowed values go from 0 up to n minus 1. And so that means if n equals 1, the only allowed value is 0 for L. But if n equals 2, well, then the allowed values are 0 or 1. All right, now, while this idea of L might seem new, we've actually talked about it before in Chem 1 or even Chem 2, where often we use letters to designate these numbers. So you might be more familiar with the SPDF designation. So that's just how it matches up. If you get an L value of 0, that's an S-type orbital. And L equals 1, that's P-type. 2 is D, 3 is F. So that's where these letters were coming from. There are descriptors for what is the number value of L. All right, the third number value, the third quantum number, is M sub L, which is the magnetic quantum number. This tells you the orientation in 3 dimensions. And so it says here, it's integers that go from negative L to positive L, including 0. So that's this mathematically. But it says for any given energy level, there can be 1s, 3p, 5d, or 7. Well, this is where we're getting that from. Why was it always 3p orbitals? Why was it always 5d? Why was it always 7f? Well, if we say, well, p orbitals, we just look back here, okay, p orbitals have an L equal to 1. Well, that means negative L is negative 1. And then we go up by 1 until we get to 0. So negative 1, 0, positive 1. Oh, there were 3 possibilities, 3p orbitals. For the d orbitals, where L equals 2, we'd have negative 2, negative 1, 0, positive 1, positive 2. Oh, there were 5 possibilities. There are 5 d orbitals. All right, so that's where that was coming from. It's this m sub L. All right? Now, if we put that all together into a giant table here, you can see the possible levels. So for the first level, the only possible value of L is 0, which means we only have S, so the 1s. And because there's only the only value of m sub L is 0, there's only one possible, so that's why it's just one orbital in that entire first row. In the second row, well, the L value could be 0 or 1, which means we'd have S or P. Well, here's the 1s orbital, but then here's the 1, 2, 3 p orbitals, and so that's 4 total. And if you remember a little bit more from Chem 1, well, if 2 electrons go in each orbital, that would be 8 electrons total, and that's why on the second row there are 8 elements. And you can see how it builds up. The third energy level can have 9 orbitals. The fourth energy level can have 16 total if we add everything up. All right. Well, let's take a little bit closer look at those different orbitals. We said the letters tell us the shape, so let's look at those shapes. For s orbitals, this value of L is 0. They are spherical in shape. And so it's basically all depends on which energy level tells you how large is the sphere. So the 1s is kind of small, the 2s is a bit bigger, the 3s is bigger still. It would just keep going. When they say contour models, that means take the dots and even them out. All right. Now this other stuff here, again, not s orbital is on the AP test. This stuff about it, not. But it says for an ns orbital, the number of peaks, meaning the number of places where it's most likely for an electron to be, is equal to that number n. And then n minus 1 tells you how many nodes there are, where there's 0 probability of finding the electron. And then as n increases, it says the electron density is spread out. Well, if we go through here, 1s, you can see, okay, there's one peak, and other than 0 where the nucleus is, there's no other zeros here. There's no place, even going out here to basically infinity, while it's an incredibly tiny probability, it is not 0. But there's one maximum right about there. Well, for the 2s orbital, that's this picture here, there are 2 peaks, one pretty close to the nucleus, right? 0 is where the nucleus is. There's one pretty close to the nucleus and one a bit further away. And here it's about 3 angstroms, so it's even farther away than the 1s. Like we said, 2s should be bigger. But then there's this node in between where there's 0 probability. So you could find an electron this close. You could find an electron anywhere out here. You will never find an electron at that exact distance from the nucleus. For 3s, it continues. 3 peaks, 3 places, or 3 kind of regions to find the electron, but then 2 nodes. One right about there, one right about there, where you'll just never find it. This node stuff, not on the AP test. It's a way of, I just don't want to leave it out in case you need it for a college class later on, saying, what do you mean there are nodes? What do you mean it's not just a ball, not just a sphere? It does get more complicated as you go. But we're just going to kind of leave it there. P orbitals have these 2 lobes. A lot of times they're kind of drawn more like that, but if you see the circles, or see the dot diagram, it's more just like 2 circles, 2 spheres, one top, one bottom. But there is a node in between them. That part you do need to know, that there's this plane in between. So here it's the XY plane. Here's the YZ plane. Here it's the XZ plane, where it's chopping the 2 lobes in half and saying, yeah, you might be on that side, you might be on that side, but you're not going to be right in the middle. Then you can see, okay, like we said, the m sub L tells you the directionality. One of them's pointing in the z direction, one of them's pointing in the x direction, one of them's pointing in the y direction. Right. So that's p orbitals. D orbitals, the L value was 2, so that means there's 5 of them. 4 of the 5 kind of looks like clover leaves, 4 lobes, and again, now they have 2 nodes. In this case, let's see, there's one here along the XY and one here along the XZ. But you just see there's 4 clover leaves, and they're just pointing in different directions. A lot of them point in, these 3 point in between the axes. This one points along the XY. And then we've got this weird 5th one, which they do give the correct term here. It is considered the one with the donut. So it looks like a p orbital where there's an up and a down, but then we have this ring around the middle, the donut, and that is also a d orbital. These 5, even though this one looks differently, they are all mathematically equivalent. They are all equal in energy, as they must be. So just even though it looks different, they're the same energy-wise. The last one is the f orbitals. The book doesn't even show you the picture, so I went and found a picture to put in there for you. There's 7 of them with L equal to 3. So we get plus 3, minus 3, plus 2, minus 2, plus 1, minus 1, and 0. So here's one that has kind of like a double donut. Here we have some that are like 6-leaf clovers, or kind of like a 6-leaf pinwheel maybe. And then these are like the double d orbitals, where it's 8 lobes, 4 coming towards you, 4 going away. Here's some more with the 6-leaf clover. So they get more complicated. The AP test definitely not going to ask you about those shapes. I just wanted to present them. So when you said, oh, they're complicated. Well, how complicated? This complicated. All right. Well, the energy of those orbitals. How do we make sense of this? Well, if you just have a 1-electron system, which is hydrogen, 1 proton, 1 electron, all those orbitals that are the same energy level, so n equals 1, n equals 2, n equals 3, they all have the same energy total. So for 1, we just have the 1s, but for 2, the 2s and the 2p for hydrogen are the same energy. The 3s, the 3p, and the 3d, each one they're the same exact energy. This is why Bohr didn't know at first there were s, p, and d and f orbitals, because he just said, well, this level's the same, this level's all the same, this level's all the same. He couldn't tell the difference. When things are the exact same energy and interchangeable, we call them degenerate. It does not mean that they're, like hoodlums and gang members. No, it's degenerate. They're equivalent in energy. Right? Well, that only works for hydrogen. So this is why Bohr's equations worked perfectly for hydrogen, but they didn't work for anything else. So, what do we do then? Well, once we have more than 1 electron, repulsions happen between them, right? All electrons are negative. They push each other away. So that means the other orbitals with their different shapes start repelling each other. And so the 2p gets pushed up in energy beyond the 2s. The 3p gets pushed up in energy beyond the 3s. The 3d gets pushed up even more. And then sometimes you get things where overlap starts to happen, where the 4s didn't get pushed up as much. It ends up being lower in energy than the 3d. So this is why when we do our configurations, as we're about to, why was it 4s and then 3d? Because the 4s is lower in energy. Now it does point out here, if they're the same type of orbital, then they're still degenerate. So the p orbitals still equal, p orbitals still equal, d orbitals still equal to each other. But they're not equal anymore to the other ones of that same energy level. 3s, 3p, 3d, they're now all different. All right. There's a 4th quantum number that was kind of determined in the 1920s, because people figured out, well, wait a minute, if we end up with 2 electrons in the same orbital, say it's a 2s orbital, they don't actually have the exact same energy. They're off by a little bit. And so how can we explain that? Well, it's explained because, well, electrons have a charge and they spin. And charges that spin in a magnetic field line up with the magnetic field, either align with it or opposite to it, and that changes the energy a little bit. So that leads us to our 4th quantum number, m sub s, which is the spin quantum number. It only has 2 possible values, plus 1/2 or minus 1/2. This is for electrons. It has 2 values. Other things have more values, but we're going nowhere near them in this course. But electrons is either plus 1/2 or minus 1/2, and we call that spin up or spin down. And we represent that often with an up arrow or a down arrow, which we'll get to when we do configurations here. Just kind of looking at the clock to see if I should make a 3rd video or continue. I think we're going to continue. So how do we address this thing about the quantum numbers? Well, that's where we get the Pauli exclusion principle, which it actually can still be stated more general and more complex than this. But what we're going to go with is no 2 electrons in the same atom can have the same set of 4 quantum numbers. You can't have the n, the l, the m sub l, and the m sub s all the same thing, because that means they're the same electron and then they're not 2 different electrons. So something has to be different. They can have a different m sub s. So one is plus 1/2, one is minus 1/2. Okay, then the other 3 can be the same. Or if they're both m sub s plus 1/2, both up arrows, Well, then that means maybe the m sub L has to be different. Maybe it has to go to a different p orbital or a different d orbital. But they can't be in the same one and still have the same spin. Something has to be different between the four numbers for any two electrons. All right? Well, this gets us into electron configurations. Where do we put the electrons? What energy level are they in? What orbital are they in? How many electrons are in that spot? So we call all that the electron configuration. The most stable configuration is what we're going to get for the ground state. So a lot of times on the AP test, they'll say, what is the ground state configuration for this atom? That means write the electron configuration where everything is in the lowest possible energy without breaking any rules. So if we get this, we get each part of the configuration has these components. We have a number out in front that tells you the energy level. We have the letter that tells you the type of orbital, S, P, D, or F. And then we have a superscript number that tells you how many electrons are in those orbitals. So in this case, we're looking at the 4p orbitals, and there's 5 electrons in that area. Right? We can also do electron configurations where we represent the electrons not just as a total number, but as individual electrons represented with arrows. We usually use half arrows or harpoons because they're easier to draw. But we have up and down. That's for the Pauli rule. The up is your plus 1/2. The down is your minus 1/2. The box is the orbital. That takes care of your other 3 quantum numbers. So this is where we're saying if we're applying the Pauli rule, you can't have 2 up arrows in the same box. You can't have 2 down arrows. It's got to be 1 up and 1 down. That tells you that the quantum numbers are not all the same thing. Right? So for lithium that has 2 electrons in the 1s, it's 1 up, 1 down. And then it has a third electron in the 2s orbital. So it's just there's an up arrow and we stop. By convention, we always start with up arrows. We just do that. All right, we also have something called Hund's rule. What if we have more than one orbital that's equal in energy when they're degenerate orbitals, like the p orbitals or the d orbitals or the f, and we have more than one electron? How do we fill those boxes? And so Hund's rule says when filling degenerate orbitals, we get the lowest possible energy when the number of electrons with the same spin is maximized. In other words, we get a better distribution, a better energy, if we spread out the electrons in the available boxes first before we pair them up. So if we look over here, boron is 2p1 at the end, so there's just 1 electron here. Carbon is 2p2. Well, Hund's rule says to get the lowest possible energy, put the first electron here in this first box. The second one is going to still be an up arrow, but it's going to be in the second box. And then for nitrogen, which is 2p3, up, up, up. All up arrows, but they're spread out in the different orbitals. Then, as we keep filling them, they skip down to neon. Then we'll pair them up until that orbital's filled, and then we'll jump up to the next one. All right? So it says here, for a set of orbitals that have the same sublevel, there's got to be 1 electron in each orbital before you start pairing, and the electrons are going to have the same spin as much as possible, so that's why we go up, 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 and then down, down, down for a p orbital. If it's the d orbital with 5 blanks, you'd say up, 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 and then down, 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 down. Right? We can condense these configurations because you'll see we'll do lots of practice in class on this. But if we do the, 1s2, 2s2, 2p6, 3s, 2s, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, we're going to go in the same order over and over and over, and we get bored of that. So to condense them, this is sometimes called the kernel method, because kernel means core, where we use the noble gas as a core that says all the electrons that noble gas had, yeah, they're on the inside. We don't have to write them. We're just going to sum them up by putting the noble gas in brackets. Has to be the noble gas. Then we'll put the valence electrons, the ones that are outside that noble gas, we'll put them after the core. So lithium is the helium core and then 2s1. Sodium is the neon core, 3s1. Potassium is the argon core, 4s1, and so on. This actually helps you see, well, why are these elements, these are all the alkali metals, why are they similar to each other? Why do they have similar properties? Because they all end with this S1 configuration. And because they all end in with that configuration, they will do similar reactions because of that, have those similar properties. All right, so this is good to shortcut. Yep, so there we go. Transition metals, they get a little bit tricky. So just going to remind you here about the rule we talked about in Chem 1 and Chem 2, that the d orbitals, because there was that overlap, and when you're going across the periodic table, you go down a number for d orbitals. So we went from 4s down to 3d, but then back up to 4p. And then for the f orbitals, they're 2 below. And so it says here, potassium's number 19, so you might say, oh, after 3s2, 3p6, okay, 3d1. But no, we do 4s1 because the 4s came first. So transition metals, they fill the 4s first, so 4s2, and then they'll start filling in the d orbitals. So here, manganese, 4s2, 3d5, and then zinc, 4s2, 3d10. Now there is an exception I want to add here. It's not on this PowerPoint, but if you have ions, where you are, for the transition metals, where you're removing electrons, for there it actually switches. When you remove electrons, you remove from the 4s first, and then if you keep removing more, then you remove from the 3d. So it's a little bit backwards there. So the 4s gets filled first, but it also gets removed from first for a transition metal ion. So if we had like a manganese plus 2, where we remove 2 electrons, it would be argon core and then just 3d5. The 4s2, those are the 2 that would get taken away. We'll do more practice with that in class. I just wanted to highlight it here to make sure I did it. Lanthanides and actinides, same thing. They're the F sublevels. They're 2 below, so the 4F doesn't show up until the 6th row of the periodic table. The actinide series are the 5F. They don't show up till the 7th row. So if we look at that here, this is what we would call the long form of the periodic table, where everything's spaced out evenly. This is what the periodic table really should look like. And so you can see, okay, the s orbitals are over here on the left. Excuse me. You can kind of imagine that this is helium right here, that it can kind of fit right there. And then, okay, yeah, there's my 2 elements, the 2 electrons that fit in each s orbital. We have the p over here on the right. There's the 6 blocks for the 6 electrons that can fit in a p orbital, and the 3 of them, so 3 times 2 is 6. There are 5 d orbitals. If they hold 2 each, that's 10. So here's those 10 blocks here. And then the 7 f orbitals could hold 14 electrons total. So here are those 14 columns right there. So this is what it should look like. But, well, that's kind of a really long stretched out thing. Wouldn't look so good on the wall. It would take up a lot of space. So what we often do is make this the medium form of the periodic table, where the F block gets cut out and put at the bottom, because then it fits on a piece of paper or a poster much, much more easily. And so you just have to remember, oh, it cuts out, and there's usually a little arrow thing or some stars that tell you, oh, right here, go down. Now you may notice, depending on which periodic table you have, sometimes the cutout is right here between S and D, and sometimes the cutout is right here after this first D electron. And both of them are valid. Both of them are done for a good reason. There is a committee in Europe working for IUPAC, the people in charge of what's the name of the elements and how do we organize stuff and all that, International Union of Pure and Applied Chemists, who are currently debating, I think they might be on hiatus now, but they're going back and forth. Should we come up with an official decision of where the cut should be made? Because if you look at the configurations, this was a D1, so it makes sense to put it after there, but then it also makes sense to put it here. There's good reasons for both, and no matter what decision they come up with, lots of chemists will be upset. We'll just wait for that decision and have fun that day. All right, but anyway, this is the way that we usually show it. It's our medium form of the periodic table. And you can see, okay, if we're going to get configuration, say for selenium here, we will, most of the time we will use the kernel configuration. So we'll say argon is the noble gas that comes before it, so argon core. Then we'll just go left to right. Here's the 4s, and we fill up both boxes, so it's 4s2. Here's the 3d, because we drop down an energy level. We fill in all 10 boxes, so it's 3d10. And then here we go into 4p, and we only go 4 boxes in, 4 electrons, so it's 4p4. And then we would stop there. All right. There are some anomalies on the periodic table. So here it's probably hard to zoom in. This table is in your book. You can look it up. But there are some weird ones. People often talk about the special stability of a half-filled orbital. And really, that's just Hund's rule. Because Hund's rule said we get the lowest energy if we can maximize the spins that are the same direction. And you maximize the spins that are the same direction if you have completely filled up everything with just the up arrow, which means it's a half-filled level. And so there's a few cases where even if we would do 4s2 first, well, then it changes where we're not going to just go like that. Maybe we're going to move one of those s orbital electrons to help make the d orbitals half-filled. So one of those exceptions you can see here is chromium. Normally, if we just did our normal one, we'd say, okay, chromium, 4s2, 3d4, done. But the real configuration, by experiment, is an argon core, 4s1, 3d5. You say, well, why is that? Well, they're close in energy, and by moving that electron to the 3d, this has become half-filled and gotten a more energy stability from having that Hund's rule maximum spin in the same direction. And so it's not much different. This is sort of the same reason of, well, why can we remove these electrons from the 4s first? Because they're still very close in energy. This also happens with some F-block elements. It happens with other d orbitals. Also on that first row, if we look, copper's another one. Instead of 4s2, 3d9, it becomes 4s1, 3d10. Palladium's another weird one. It's not even 5s2, 48. It's just 4d10. There are no 5s orbitals in palladium. So usually, I'm going to say we don't need to memorize these. We just need to know that they're there, so if we see them. But I'd say chromium and copper, because they're in that first row of transition metals, and they're sort of really well-known exceptions, I'd keep an eye out for those just to make sure you have those two in your back pocket of, yes, I remember those two are weird. It's 4s1, 3d5 and 4s1, 3d10 to either be a completely half-filled d orbital or a completely filled d orbital. All right? That's going to be the end of chapter 6, so I hope this was useful. Obviously, more practice in class, in lecture, and in lab. Hope to see you guys soon.